let's take a look at the boot init sequence that your Red Hat Enterprise box travels through whenever it is started. We'll log in as root to the SUSE Enterprise 10 box, as it hosts the VMware instance that we're interested in finding out more about. Then we'll launch the VMware Server Console. We'll connect to localhost, and then we'll navigate to our various instances and focus in on RH5_instance1. Now we'll power this machine on, and it'll take us to the main menu, so let's go ahead and power this on. And once at the main menu, we can decide which run level we'd like to boot in. We'll just interrupt the process by moving to or pressing any key. And here's the main entry. Now, in order to interact with the main entry, we'll need to specify a password as indicated below by pressing P. And once we've indicated the correct password, we see the remainder of the options, including E to edit, and A to modify kernel arguments, and C to go to a command line. In order to boot into different run levels, edit the startup line for the kernel, but you need to determine which run level is ideal for you. Supposing you want to do some system administration tasks on your box, you then indicate single or the number 1 anywhere on the command line. So we'll edit the entry, and then simply indicate either 1 or single as we've done throughout our installations. Press enter and then B to boot, and this will boot the system into single user mode. So if you need to perform administrative tasks such as backing up a file system or perhaps the management of logical volumes, then enter into single user mode, because that mode assures you that networking services are not started and you'll be the sole user or lone user connected to the system at that given time. So single user mode loads services that are necessary for you to interact with the system, including mounting file systems and local services, such as UDEV, for example. It does not provide a GUI, but it does mount the various file systems and provides a limited shell. So this is single user mode. We can interact with the file system, make changes, etc. Now this is also the mode that you'll connect to or launch into in the event that you've forgotten root's password. So if for some reason you're unable to log into your system as root, the super user, you'll want to boot your system into single user mode and then execute the password command, which will allow you to change your password for root. Because by virtue of entering single user mode, you are the user root. So we're currently connected as root without being prompted for authentication, which is why you should guard your grub environment to ensure that unauthorized users who access your system are unable to make changes, boot your system, and take over your box. In other words, we wouldn't want unauthorized users to compromise your system simply because they found an easy way to get in, which is to physically gain access to the box, boot into single user mode, and change root's password. But again, if, for example, perhaps for the exam or just for your own intents and purposes and knowledge, you need to change root's password, single user mode is that mode that you should use. Now from single user mode, you can execute the init command to propel yourself into another user mode, such as run level number 3. The init process is the first user space process which runs, and it always has the process ID of 1, regardless of the mode that you enter. So for example, if we execute PS, which lists processes in the process table, followed by EF grep init, this returns the fact that init's running as process ID 1, and there are other processes that reference init. So init's accessible as process ID number 1. It's always the first process, and it is the process that calls all other processes to set up your Linux environment. But let's step back a little bit. How about from when you've powered your machine on? Well, when you power on your machine, the first thing you do is you power it on, and then the system's BIOS, or basic input-output system, takes over. It checks your hardware. So the BIOS is responsible for checking RAM, keyboard, perhaps your mouse, storage, etc., to be sure that these components are connected and properly configured and there are no basic errors. Once your BIOS has set up your environment, it finds the first bootable device, which may be a CD-ROM, a DVD drive, a USB pen or stick, or perhaps a SCSI, IDE, a TAPI, SATA hard drive. So after the BIOS performs its check, the next step again is to consult the bootable media. The bootable media may in fact be, again as mentioned, CD, DVD, USB, pen, stick, hard drive, so on and so forth. After the BIOS has consulted the bootable media, it searches for the master boot record, so it searches for the MBR. So on the bootable media, it's searching for the master boot record, the area which happens to be 512 bytes that stores the bootable code. Now there's some legacy reasons as to why the master boot record on PCs is only 512 bytes. And for those legacy reasons, new PCs must adhere to the master boot record specification. So even modern hard drives maintain a small 512 byte area known as the partition table, which is the boot area, which describes the partitions on the disk and sets up the menu, or provides information to set up the menu, which provides you access to your system. Whether your operating system be Windows, Linux, FreeBSD, so on and so forth, so long as you're using a PC, the following applies. You power it on, the BIOS checks hardware, it sets up the default bootable media by searching its master boot record for boot code. So in the MBR, you find boot code. That boot code is enough, and it's called stage 1. In this case, it's stage 1 grub, is enough to set up the remainder of the grub environment. After the boot 1 stage, or the boot code, stage 1 code that is launched, stage 1.5 grub is consulted. So grub stage 1.5 is consulted, which presents a menu to the user. From that main menu, we select the operating system that we'd like to boot. So from the menu, we select OS, which for our environment is a lone entry, a single entry. Now in the event that you're wondering where the menu files are maintained on the system, let's df-h to show you. Beneath the root subdirectory, and in fact also beneath boot, it needs to be in the boot section, but etc has a link to it, there's a subdirectory named grub. So beneath boot, which is symlinked beneath /etc, we navigate into grub, are the files that are used to boot the system. You'll notice that a stage 1 file is exactly 512 bytes. This file sits on your bootable media, the first hard drive that's used to boot your system, whether SCSI, SATA that is, IDE, so on and so forth. This stage 1 code is exactly 512 megabytes, 512 bytes that is, and it's enough to consult stage 1.5. Stage 1.5 sets up the appropriate file system, whether you're booting from a CD-ROM using ISO 9660, a FAT file system, XFS, or even E2FS, which is the file system used with ext2 as well as ext3. So from stage 1, stage 1.5 is consulted. Stage 1.5 provides the driver information required to provide access to your E2FS or ext2 or ext3 file systems, in particular boot and root. Once stage 1.5 is loaded, we move on to stage 2. Stage 2 sets up the environment and then calls the init process. The init process, if we do a which init, is located in SBIN. It's a system binary. In fact, beneath SBIN you'll find system binaries that require generally root access to execute. Init is a special process. Its job is to set up the Linux environment. Init reads beneath etc, and just to divert for 1 second, we did mention that beneath etc there's a symlink for grub.conf. That's this file. Grub.conf is referenced from boot grub.conf. Grub.conf is a configuration file read by grub, which contains the menu items that you see on your screen when your system starts, and some sensible settings for default, timeout, splash image, so on and so forth. So here's that grub.conf. It includes a default entry of 0, which means the first menu item is to be loaded after 5 seconds, which can be modified, of course. A splash image is shown, which is pulled from the first hard drive from the first partition /grub and there's a file beneath the grub directory that's dumped to the screen, and it's compressed using GZ format. A hidden menu is maintained. A password is associated with the menu, which is what we have to specify in order to make changes to the grub menu. And the first menu entry, title Red Hat Enterprise Linux, which launches from the first hard drive HD0 in grub terminology from the first partition 0. The kernel is referenced from VM Linux, and it's version 2618 with root being the label and some options passed in, with an initial RAM disk which has additional drivers necessary to set up your storage environment, which means to mount the remainder of your file systems, whether LVM, RAID, so on and so forth. So that's the grub.conf file, which is symlink. But back to init tabs. After the grub or the bootloader has done its job, which is the handoff to init, init reads a special file in etc. It's called init tab. Init tab is a table file which contains initialization entries. An important entry is the ID entry that you see here. It includes the default run level in the second column. So ID :3 :init default means to the init process that the system is to be booted in run level number 3 by default. But there are other entries. For example, the system is initialized using the following script, etc rc.sysinit. So there are some generic entries that pertain to all run levels that execute from rc.sysinit. There are additional entries for various run levels, 0 through 6. Now, Linux, which is a derivative of Unix, maintains multiple run levels, generally 0 through 6 if it's a System 5-based system. There's a description of each run level within that init tab file. 0 halts the system. So for example, if you were to execute init space 0, the system would be halted. In other words, the services would be stopped and your hard drives would be parked. 1 is for single user mode, which is a mode that we're currently in. So if you execute init space 1, regardless of the mode that you're in, it will propel you into single user mode. It's a great way to switch or shift from perhaps run level 5 or 3 multi-user modes to run level 1. 2 is multi-user, but it doesn't support or execute NFS. Run level 3 supports all networking services including NFS, and it's the text-only multi-user mode. 4 is unused. It's a mode that can be used by ISVs or software providers, and you can copy the entries from run levels 3 or 5 to set up 4 to suit your needs. And run level 5 includes everything in 3 plus X11 or X.org, meaning a graphical environment. Run level 6, if you execute init space 6, simply reboots the system. So it's a quick way to execute reboot instead of typing reboot. So these are your 7 run levels that you'll find on a System 5 compliant Linux or Unix system. And this Red Hat Enterprise system adheres to System 5. Now for each of the run levels, there are a series of scripts that are to be executed below certain directories. For example, for run level 0, the scripts beneath the 0 directory is executed, and for 1 through 6, ditto. So there are directories beneath etc rc.d that correspond to the appropriate run level that you are attempting to enter. What happens if you execute Control-Alt-Delete from the console? The default reboots the system. This is an item that we tend to comment so that an unauthorized user who has access to the system doesn't inadvertently or purposely reboot your system while it's up and in production. There are some UPS entries, programs that can be run if you have a UPS connected. And towards the bottom of the init tab file, there are entries for the min-getty process. This min-getty program is responsible for providing you the consoles that you see on Control-Alt F1 through F6. Notice that the min-getty process is set up to run in all run levels. It's set to respawn, which means if the process dies, init will automatically restart it. It runs sbin min-getty, and it binds min-getty to various consoles such as TTYs 1 through 6. You can always tell the TTY that you're on by simply executing TTY. Additionally, if we are to enter run level number 5, the preferred display manager program is executed. In other words, a program which allows us to launch our display manager, whether it be GNOME, KDE, or some other display manager, is presented to us so that we can make that choice. That's basically your init tab file. A man space init will give you more information about the entries in the file, but just know that it controls the startup of your environment, it loads some default scripts, and it has files that are executed, or scripts that are executed per run level, and it's also responsible for spawning and respawning the MinGetty console program, which provides us with shell-based access to 6 consoles, plus on the 7th console accessible using Control-Alt-F7, the graphical environment in the event that we have entered run level number 5. And this is the main reason why, especially this Getty section, MinGetty section, why init always runs, because it needs to constantly pay attention to whether or not n number of MinGetty processes are running. So if you ps-ef grep at any time, you'll see that init's running, and if MinGetty, if we ps-ef grep MinGetty, is terminated for whatever reason, and it's currently not running because we're in single user mode, notice the list of user modes includes 2 through 5. So in user mode number 1 we don't have, or single user mode, we don't have multiple MinGetty processes, but if we're in any nodes 2 through 5, any of the nodes 2 through 5, then the init process will ensure that MinGetty is always respawned in the event of failure. So again, when you start your computer, you power it on, there's a handoff to the system BIOS, which then searches your storage devices for the default bootable storage device, and it searches for the MBR, the master boot record, where it finds Grub, the Grand Unified Bootloader, and this is stage 1 Grub. After that, stage 1.5, or Grub stage 1.5 is called, then Grub, and stage 1.5 provides file system access. 1.5 includes enough code to support the file systems on your system. So if you're using SUSE Linux, for example, you'll see that there's a RiserFS stage 1.5 Grub file available. After stage 1.5, Grub consults stage 2, which then consults the init process. The init process reads etc init tab, and then it sets up the appropriate run level. Another thing we should note is that in higher numbered run levels, programs that were launched in lower numbered run levels will always execute. So if you enter 3, programs that typically execute in 1 and 2 will execute. Ditto for 5. 5 executes everything in 1, 2, 3, since 4 isn't used, it can be ignored, plus whatever is executed in 5, with the exceptions being 0 and 6. 0 shuts the system or halts it, 6 reboots the system, both of which actually shuts the services, parks the hard drives, and sets the system up to be rebooted so that you don't lose data inadvertently. So that's your boot init process. Again, etc/init tab is the main initialization file, and it's always running its process ID number 1, and sometimes when you have boot up problems, you can take a look at the grub configuration file located beneath etc as grubconf, which is symlinked to /boot/grub, and by examining the contents of this file you can determine whether or not something's been changed. For example, if you know that your system typically boots from the first hard disk, first partition, then you should see HD 0,0. If you see that, say, HD 1,0 or 2 or some other numbered set for the hard disk as well as the partition, then you know there are problems booting your system, or you will have problems booting your system, and you'll then need to either attempt to boot from the hard drive or use the first CD-ROM and boot into rescue mode to make changes to the grub configuration file. Also, you may see problems, let's say, with the initial RAM disk. It may be commented out or missing altogether. Ditto for the kernel. You may see a wrongly numbered kernel version, or options such as read-write or no read-only, so on and so forth. Again, the kernel's files are located beneath the boot directory. You'll find them in there, vmlinez, as well as the initial RAM disk file. These two files are specific to the hardware architecture on which we're operating, in this case i386, and they contain the appropriate drivers necessary to set up the environment. In addition, you'll find a system map and a config file. Config file contains all of the entries that were enabled and disabled prior to the compilation of the kernel. And beneath boot, you'll find, as mentioned earlier, the grub subdirectory, which contains all the files that pertain to grub, plus the splash background that's displayed, the Red Hat splash background in this case, splash xpm.gz. There's a menu.list file, which is really a symlink to grub.conf, which is the main menu, device map, and various drivers for stages 1.5 for the different types of file systems supported by grub, including, as you see, XFS, VFAT, RiserFS, ext2, which supports ext3, Minix, so on and so forth. So within the realm of booting your system, know that there's always a handoff to init after grub, which loads the different services based on the specifications in your init tab file. Now we did mention that init tab references specific directories for the different run levels. For example, what exactly happens when you enter run level number 1? So if we navigate into etc, and we'll just kill this screen here, rc.d, we'll see various items if we lsltr. There are entries, directory entries that is, for each of the run levels. Additionally, there is an rc.sysinit script, which is consulted in every run level, an RC and an RC local script, which can be used to launch programs outside of RC sysinit and the distinct run level scripts. There's also an init.d directory. Init.d houses all of the programs or all the daemons and or services that run on your computer, from NFS to kudzu, which detects hardware, to first boot, to SSH, to winbind. All the programs that you can run on your box are located, or services that is, that can be executed by init are located beneath etc, rc.d, init.d. Each of the run levels simply symbolically link to the scripts that are in etc, rc.d, init.d. So for example, in rc1.d, for the first run level or single user mode run level, here are the programs that run. Additionally, each program, although symlinked to the init.d directory, is prefixed with either a K or an S, followed by a sequential number. So now LSL, for example, of start or S star reveals all of the start scripts. LSL of K star reveals all of the kill scripts. S scripts are start scripts, K scripts are kill scripts. So when you enter a run level, certain programs are killed and other programs are started. When entering run level number 1, for example, here are the 3 programs that are started: single user mode, CPU speed, and LVM2 monitor. Also, when entering run level number 1, here are the programs that are killed. Most of the programs that run in other run levels, such as multi-user levels 3 and 5, are killed in order to enter run level number 1, to be sure that there are no connected users across the wire, of course. Now let's take a look at rc3.d, which is the default run level on this system. You'll find more of a balance of kill and start scripts. So an LSL of S star piped to WC-L reveals 44 start items. So 44 services or 44 programs which handle anything from your keyboard mapping to SSH to winbind to kudzu to AutoFS to NFS are started, and they're started in various orders. Scripts that are started or killed with lower numbers occur earlier in the start or kill process. So for example, a program with start 25 is executed before a program with start 26, and ditto for kill scripts. An LSL of K star for this run level reveals very few items. We can pipe it to WC-L, and you'll see in comparison very few items, 27 entries versus 44. So for your main run levels 3 and 5, you'll find more starts than kills, and for your other run levels such as reboot and halt, you'll find more kills than starts. But again, that's how the System 5 framework works. These are just symbolic links with different names, one level up, one level down into init.d, where all of the scripts reside. And whenever you install programs on your Red Hat Enterprise box that are System 5 aware, they place their entries beneath init.d and the appropriate run level. And again, there are certain items that execute globally from RC, RC-sysinit, and RC.local that apply to all run levels. So the System 5 framework is very straightforward, very easy to follow. So long as you know to navigate beneath etc rc.d, it's self-explanatory. We'll take a look at the different run levels as they're presented, as well as init.d, as well as the other three scripts which run regardless. And with that in mind, you'll be able to program different daemons and services that don't have scripts or programs to set themselves up automatically. You'll be able to set them up automatically. And there are many such programs out there that just don't ship with System 5 scripts because of the variations of Linux available. So they leave it up to the systems administrator to specify how to start as well as stop the scripts. Another unique thing about the scripts that you'll find in init.d is that they support functions similar to services within a Windows environment, such as start, stop, restart, reload, so on and so forth. So they're basically analogous to services within a Win environment, and they're located beneath init.d. So again, to recap, you power on your system, the BIOS takes over, it consults Grub, in the case of Linux of course, or your bootloader for Windows or some other OS. Grub then consults init after it steps through its phases of 1, 1.5, and 2. Step 1 being 512 bytes to fit within the master boot record space. 1.5 provides the appropriate file system support to be able to read the contents of your hard drive. And then 2 sets up the menu and provides the options necessary to start the system, which calls init. Then init reads the various run levels, starts and does some housekeeping, and presents your environment in either run level 3 or 5. So currently we're in run level number 1, single user run level, and we also mentioned that whenever you're logged into a terminal you can type TTY, or there is a way to determine where you're connected to. Because this is a VMware instance and we can look at it within the sort of window that we're in, which is another Linux box, it appears as if we're truly on the console. As far as the Red Hat Enterprise instance is concerned, we are on the console. So we're connected currently to dev console. Whenever you're in single user mode, you are at the console because there is no networking. So again, if you make a mistake across the wire, let's say there's a server across the country, across the state, across the world, if you make the mistake of initting into single user mode, you will no longer have access to that system. You will need someone to physically connect to it and make the change for you to a network capable or network ready run level, unless of course you have some other means, out of band means of connecting to the system, such as dial-up into a serial port. Now to move to a different run level, such as run level 3, simply execute init space 3. This will propel us into run level number 3. Different scripts will be stopped, and the majority of the scripts in init.d beneath etcrc.d will be started. As you can see here, these are the programs that we typically see executing whenever we start our Red Hat Enterprise box. Anything from IP tables to AutoFS to NFS to SSH to SendMail or optionally postfix to other programs. Now we're in run level number 3. If we log in, and in run level number 3, or for that matter in any multi-user run level, you must authenticate to the system. Whereas in single user mode, you're not required to authenticate to the system, which is why it's imperative you protect your Grub startup environment with a password. So now, once we're in, it tells us which terminal we're in, we've logged on to, and it's now dev TTY, a teletype terminal as opposed to the console. This is console or terminal 1 of 6 that's made available. So there are 5 other consoles that can be used to run other programs. This isn't dev console, and it's now connected to the network. We can actually interact with other folks on the wire. We can ping out, for example, to the default gateway. We're now on the wire. It's multi-user mode. Other folks may be SSHing in. Bottom line is we're now in multi-user mode, and there's a program which tells you the current run level. It's called run level. tells us that we're currently in 3, but we were previously in single user mode. So use a run level utility to determine the mode that you were in before and the mode that you're now in. And you can alternate between these run levels by simply executing init followed by the run level number. Now if you'd like to influence the run level that you enter during boot, as mentioned earlier, simply specify the number or the keyword single. So let's reboot, and this time we will make a change to boot ourselves into run level number 3 explicitly, which will perform no differently than the default, since the default is run level number 3, or we could default to single, but we've already done single enough times. So the system's rebooting. We'll see the VMware BIOS momentarily, and we can quickly step through what typically takes place on a standard PC. Again, when we reboot the system, an initialization of 6 is sent, which stops most of the services. Here's the BIOS. It checks hardware. It takes us to the boot menu, grub, stage 1, then 1.5, then 2. Now we have a menu. We can then interact with this menu by typing in a password, and if it's correct, it will give us access. We'll try it again. And then once we have access, we'll edit the default kernel boot up label. You generally don't want to edit the root entry as well as the init.rd entry, especially the init.rd entry. Otherwise, you may risk or run the risk of not being able to boot your system. So let's edit this entry, and we'll just indicate at the end 3. Any run level that you'd like to enter, just simply specify the number, such as 1, 2, 3, 4, or 5. Or the keyword single. Either or will do. So if we indicate 3, this will be the default. We will press B now to boot, and this will propel us into run level number 3, at which point the system will be up, available, accessible to all the users on the network, providing IP connectivity has been addressed, and we'll be able to serve our user community. So that's a little bit about the BIOS/grub/init framework. That's the sort of environment that your Linux box is accustomed to operating within. So now we're coming up. It's detected that the hard drive supports write-through caching, and now you see different services. The clock has been set. UDEV has been loaded to detect any connected hardware, including USB devices. The local file system has been brought up, and it tells us init is entering run level number 3, and it's going to set up a few more services. Different loggers are coming up. NFS was brought up. SSH, sendmail, the @daemon, Anacron, all of the key programs that make your Linux box tick. So that's a little bit about the grub init environment.